I hope y'all are doing well today. Um, do you have any questions before we get started? All right. Today we're going to look at 5.2. We may have an opportunity to go on and continue into section 5.3. So we'll see how we go from there. And that's our plan for today. Um, yeah. So let's get started with section 5.2. Now, this section covers what we call the addition rule. And also the concept of a complement of an event. It's complement with an E, not an I, so we're not saying nice things about it. We're finding its adjacent group or adjacent set of events. Yeah. Anyway, so a couple of ideas that we want to start off with here. First of all, let's look at, before we dive into the additional, let's look at the intersection of two events. And the language that we like to use here would be, for instance, the probability of A and B. And the key word there is that we have and between the two events in parentheses. So this is the probability that events A and B both occur, or both are successful. Sorry about that. All right. So in this case, we start off with two different events, A and B. We want to figure out under which circumstances would both events be considered a success. For instance, a hat contains the numbers 1 through 10. Event A is the outcome where, or set of outcomes, where we select one of these numbers at random and the result is an odd number. And event B, we select one of these numbers at random and the result is a multiple of 3. Okay. Now, if the result is odd, we think of which numbers between 1 and 10 would make that true. Well, we know 1, 3, 5, 7, and 9 are all of the odd numbers that are between 1 and 10. Okay. Same thing with multiple of 3. In this case, we're looking at the numbers 3, 6, and 9. So the question is, if we want the probability of A and B, when we look at the number of ways that both events can be successful at the same time, it means we're trying to determine, are there any numbers that we could draw for both events A and B would be considered a success. Now, in this scenario, what it really amounts to is, are there any numbers that A and B have in common that would make both of them successful? And do we have any numbers where that's true? Three and 9, yeah. So these have 3 and 9 in common. Okay. So there's two different numbers for which both of these would be considered a success at the same time. Out of how many possible numbers? Well, we have 10 total. So there's a 2 out of 10 chance both events A and B would be successful simultaneously. Okay? So again, we're basically looking at, when we say A and B, we're looking at where do these two events overlap. Okay? And they overlap in these two numbers in particular, 3 and 9, because 3 and 9 appear on both lists. And we can reduce that to 1/5, or we can just turn it into a decimal, which would be 0.2. Okay? Now, the other expression that we want to look at in this section is what we call the union of two events, which is A or B. In this case, when we say A or B, the idea is that which value, or how many, how did I say it before? I'll try to remain consistent. This is the probability that either A or B or both are successful. Okay. So that means either one of these could be successful, or both of them could be successful. So we're not looking for the overlap, or in this case, we're looking at more of what we'd call a combination of the different outcomes. Okay. So going back to our picking numbers from a hat, if event A is our odd numbers, and event B is our multiples of 3. Okay, what's the probability of A or B? Okay. Now, again, when we say A or B, that means either A or B or both are successful. So between A and B, how many different numbers do we get from the 10 that are total that are in the hat? What are the different numbers that A or that we could potentially draw from the hat that either one of these, at least one of these, will be true? So we would say at least one of these is true if we draw which numbers? Okay. This one is a little bit more tricky than the other one, that's why I did it second. But the idea is that we have 5 numbers here and we have 3 numbers here, but there are some that are in common that we saw in the last question. So at least one of these is true if we draw 1, 3, 5, 6, 7, and 9. You're on the right track, Haley. You're almost there. we wouldn't count the 3 and the 6 the 3 and the 9 twice. The 6 is only there once to begin with, so it would be 6 out of 10. So as long as we choose one of, it's okay. As long as you choose one of these 6 numbers, a 1 would make event A successful, 3 would make either one of these successful, 5 would make event A successful, 6 would make event B successful, 7 would make A successful, and 9 would make both successful. Then we can say at least one of those 2 events will be successful if we choose any one of those 6 numbers. So that's 6 out of 10 probability, or 0.6. Now, the nice thing here with the union of 2 events is that we have what's called the addition rule, which will make it a little bit easier to calculate exactly what this probability is going to be. So our addition rule says that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay. Let's look at the above example. What is the probability of this event A? So we take the number of ways that A might be true divided by 10. Again, we're using the same general approach to probability that we talked about last time, which is we count the number of ways an event could be true out of the total number of possible outcomes. So how many different numbers could we pick that would make event A true out of the 10 total? Five. Yeah, 1, 2, 3, 4, 5 terms here. There's a 5 in 10 chance that A is successful. So the probability of A being successful or A occurring is 0.5. What about the probability of B? What would we get there? Okay. Event B, we have 3 possible outcomes there for which event B would be true. 3, 6, and 9. So that would be 3 out of 10, or 0.3. And probability of A and B This is actually what we worked on the other side of the page. And here we said that probability of A and B was 2 out of 10. Okay. And again, that was because that A and B both have the 3 and the 9 in common. So they have two numbers in common, so it's 2 out of 10 chance that both would be considered a success simultaneously. And so finally, we can put those together according to our addition rule. So we'll say the probability of A or B is equal to the probability of A, which is 0.8, no, 0.5, sorry, I'm getting ahead of myself, plus the probability of B, which is 0.3, that makes 0.8, and minus the probability of A and B, which was 0.2, and so 0.5 plus 0.3 is 0.8 minus 0.2 gives us 0.6. And notice that 0.6 is exactly the same number we got before. So whenever we want the probability of A or B, where we have this, what we call this union of two events, we could either count it logically if there's a small enough amount of data there, or we can go through and just calculate the individual probabilities here and combine them together according to our addition rule to get that calculation. So right there, that's really two different approaches to finding the same thing. Overall, I would recommend the addition rule because generally speaking, we're going to have more than 10 possible outcomes. It just depends on the particular event or set of events that we're looking at. Alright. Now, we look at this equation and we have P of A and P of B added together, but then we also subtract where they overlap. And it may not make sense. But the idea is that if we have P of A and P of B, there may actually already be some overlap between those. So by taking, and let me pull this down a little bit, by combining P of A and P of B, we've actually counted the 3 outcome and the 9 outcome twice, because we included the 3 and the 9 here and here. So that's 5 numbers, that's 3 numbers. Okay, combined that makes 8 numbers, but because of that repetition, there's only 6 different numbers between these two events because of that overlap where the 3 and the 9 are part of each outcome or each set of outcomes. And that's why we have to subtract P of A and B in our formula, because if we count the 3 and the 9 twice here with P of A plus P of B, we have to subtract the intersection of the two events, because here the 3 and the 9 count twice, and then we subtract it once, so now the 3 and the 9 are counting exactly once after subtracting that. Okay? Maybe a better way, and it's not often that we get to say this in math, maybe a better way to explain this would be to show a Venn diagram. Alright, so whenever we create a Venn diagram, we put the overlap in the middle, which is 3 and 9. Event A is also successful for 1, 5, and 7. and event B is also successful if we have the value 6. Outside of those, we have 2, 4, 8, and 10, for which neither event is successful. Okay? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All 10 numbers are represented in our diagram. So when we find the probability of A, A contains 5 numbers. 1, 3, 5, 7, 9. And if we say the probability of B, B contains 3 numbers, 3, 6, and 9. But if we add those together, probability of A plus probability of B, we've counted these two numbers in the middle twice. And so to counteract that, we subtract what's in the intersection, A and B. If it's counted twice and we subtract it once, now everything in here counts exactly one time. So P of A is 1, 3, 5, 7, 9, plus P of B is 3, 6, 9, minus P of A and B, which is 3 and 9. So we take these 5 numbers plus these 3 numbers, but then take away these 2 numbers. So when we added P of B, we added 3, 6, and 9, but we don't need that 3 and 9 a second time, so we take them away again. And we just add that 6 to these first 5. So 1, 3, 5, 6, 7, 9 are the resulting numbers that we end up using for A or B. I don't know if that's any more helpful, but that is what's happening here with our addition rule. Because there is this overlap of the two events, we have to account for that in our calculation of the union of the two events. If it turns out that the overlap of the two events is 0, then in that case we refer to the two events as being either mutually exclusive or simply disjoint. Depending on the different scenarios we look at, it's possible that we just don't have any numbers in common between these different elements. Okay. So let's look at another example, and here again we have the numbers 1 through 10. In a hat. This time we're going to define 3 events, A, B, and C. For event A, this time we'll use let's use multiples of 5. For B, we'll use the even numbers. And for C, we'll use the powers of 2. Now, before we proceed, we'll also want to write down which particular elements are in each of these groups. So when we look at multiples of 5, that would just be 5 and 10. Even numbers, we know that's 2, 4, 6, 8, 10. And powers of 2 is 1, 2, 4, and 8. One is actually 2 to the 0th power. That's why we include that. 2 squared is, or 2 to the first power is 2, 2 squared is 4, and 2 to the third power is 8. Anyway. So now we have 3 different events. Whenever we do our probability calculations with union or intersection, we do want to only use 2 events at a time. So we'll never say probability of A or B or C. What we could do... No, we couldn't do that. Yeah, we typically would not use A or B or C. I guess we could figure it out though, but generally we do not like more than 2 events being combined in our union or our intersection. At least we're not going to deal with it in this particular course. So. All right. So what is the probability of A? And if you want to go ahead and give it as a decimal, that's fine. So A contains 2 outcomes where it would be considered successful, 5 and 10, out of the 10 total numbers that we could potentially choose from this hat at random. So what is the probability? Two out of 10 or 0.2. Again, we're just counting at 1, 2, 2 numbers there out of 10, and that's our probability. Probability of B, 1, 2, 3, 4, 5 numbers would make that a successful event out of the 10 total. So 0.5. And probability of C, there's 1, 2, 3, 4 numbers where it would be successful out of the 10. So that is probability of 0.4. Okay. What about A and B? How many numbers do those two events have in common? Right, they just have the 10 in common here and here. So if we were able to select the 10 at random, then that means both events A and B would be successful. But again, that's only 1 out of 10 outcomes where that would occur. Okay. For B and C, 2, 4, 6, 8, 10, and then 1, 2, 4, 8. How many do those have in common? Two, 4, and 8. Good. So that's 3 numbers total out of 10, or 0.3 exactly. And finally, what about A and C? So here you have event A and event C. Those are called mutually exclusive, exactly. When we say something is mutually exclusive, the meaning of that phrase in particular means that the occurrence of one precludes the occurrence of the other. Meaning if event A is successful, that means we drew either a 5 or a 10. There's no way that event C could also be successful at the same time, because in order for A to be successful, it means we drew a 5 or 10, and neither of those work for event C. Okay. So we said the probability of A is 0.2, probability of B 0.5, probability of C is 0.4, probability of A and B was 1. Yeah. Probability of B and C was 0.3, and probability of A and C is 0. Okay. Sorry about that. That bothered me. Alright, so if we wanted the probability of A or B, we know we would take probability of A plus probability of B minus probability of A and B. And again, that's just our addition rule right there. Probability of A is 0.2, probability of B is 0.7, and A and B is 0.1. So that gives an overall probability of 0.6. So we had 2 and 5 and then subtract 1. And then the probability of A and C is probability of A plus probability of C minus probability of A and C. Again, filling in our numbers that we have above. Probability of A is 0.2. Probability of C is 0.4. A and C was 0. So this one's also 0.6. Okay. When we have two terms that are mutually exclusive, though, and this "and" expression ends up being 0, the intersection, then in these cases, basically what happens is in the addition rule, we don't even have to worry about this third part because we know that it's 0. So if two events are mutually exclusive, then probability of A and C is just probability of A plus probability of C. We don't even need that third part because we know it's 0. The book gives this as a separate formula, but I think if we just use the original formula and we are able to, or we know how to calculate each of the individual probabilities, then there's no need to have to work with the second formula. It's a simplification of the first one in one specific instance. So, yeah. Okay. I want us to look at problem 40 on page 271. And we start off with a table. Let's see, we have 5 columns and is it 1, 2, 3, 4, 5 rows. Okay. All right. Let's see. Okay. This is a table that we'll also see a fair amount of, a type of table, not this one specifically, but where they give it to us where there's two different things that we're considering. We want to look at how many people have both traits, or either one or the other, or both. So for the husband being the only one that works, that occurs, there are 172 couples where they have 0 children, 79 couples where they have 1 child, and 174 couples where it's 2 or more. That's 425 total. Where only the wife works, that's 94 couples with 0 children, 17 with 1, and 15 with 2 or more, for a total of 126. Where both spouses work, 522 with 0 children, 257 with 1, and 370 with 2 or more, for a total of, was it 1149? Yes. In our last column, or last row, is the total, so we have 788, 353, 559, and 1700. Okay. So that's the data that we're given in this particular problem. This is, whether the husband or the wife or the both work in different situations where they either have 0 children, 1 or 2 or more. And then again, we have the total for each row and for each column. Alright, hopefully we can read that okay. Alright, so let me take this page out and then we'll keep it handy. Based on this table, we'll now have a series of questions. A. What is the probability that for a married couple selected at random, both spouses work? So for how many spouses is that true out of how many total people that we might choose from, or couples that we might choose from? The main thing here is being able to read the graph. The probability of both spouses work. That's a total of 1,149. Out of our total of 1,700 couples that were studied. And we would divide from there. 1149 divided by 1,700. And so it gives us about 0.679. Okay. We are rounding, so I use the wavy equal sign rather than the normal equal sign. Anytime we round, that means it's an approximate answer. Normally here, when we're calculating these probabilities, I would say use 3 decimal places. That's generally a nice way to go. I think sorry. That was a 6. I'm just looking at my calculator again. It's 676. Sorry about that. Anyway. Alright. Question B. What is the probability that for a married couple selected at random, a couple has 1 child under the age of 18? Okay, so we look at our table. For how many couples is it true that they have exactly 1 child under the age of 18? $353. Good. Now again, we take that out of the total, 1,700, and then we'll approximate our answer there. We come up with 0.208. Part C. Sorry, I'm trying to get this centered somewhat. Part C, we got the probability that a couple selected at random has 2 plus children under 18 and both spouses work. So this time we're looking at how many of the couples fit both of these requirements, that they have 2 or more children under the age of 18 and both spouses are working. For how many couples is this true in this particular survey? So we have 2 children under 18. We know that's that column. Both spouses working is this row. And we look at where do that column and that row overlap. Because anytime it says and, we know that's an intersection. So what is the intersection of that column and that row? 370. Yeah. So these 370 individuals, couples, looking at 2 plus children and both spouses working, this is where they overlap right here at 370. Okay. And again, we calculate that value. It comes out to be 0.218. Okay. D. What is the probability that for a married couple selected at random, the couple has no children or only the husband works? Now, when we see this or statement here, what we want to make sure we do is apply the addition rule. And the addition rule says that this will equal the probability that a couple has no children plus the probability where only the husband works and minus the probability of both being true. Again, with an or statement, it has us looking at 3 different things, basically. So, for how many couples were there 0 children? $788. Yeah, 0 children. The sum of that column is 788. In how many couples did only the husband work? Only the husband working. We look at that row. We come up with 425 out of 1700. And finally, in how many couples were both of those things true, where they have no children and only the husband works? So again, the intersection of those two, basically where do those two row and columns overlap? And so we look at 0 children and then only the husband working. That's the 172 right there. Alright, now to combine these together, what I would recommend is going ahead and combining the numbers on the numerator first, because we know we have a common denominator, and then we'll go through and divide it at the end. 788 plus 425 minus 172 gives us 1041. And then we divide that by 1700, which gives us 612. So in just over 61% of the couples surveyed, either they had no children or only the husband worked. The last part of this says, would it be considered unusual to select a married couple at random where only the wife is working? Now, remember last time we said unusual will be basically less than 5%, so we'll have to calculate the probability where only the wife is working, which is the 126 times that happened out of the 1700. And that comes out to be 0.074. And so the question is that smaller than 5%? Well, no. This is actually 7.4%, so it's bigger than 5%, and our conclusion is not unusual. Okay. Certainly there is a smaller number of couples for which that is true, but it doesn't fit the statistical definition of unusual, so we can at least make that claim. Okay. Any questions on this problem? That really outlines the two different ways that we see these questions asked. which is one where we just have a list of outcomes and we have to figure out what the probabilities of each, with like we did with the numbers being drawn out of the hat. The other way we see this data given to us is, rather than just have us calculated, count up everything by hand, they go ahead and tally up everything so that we have the number for which each item is true, and then we calculate the probabilities as requested from there, and where we have this table like we did just now. So we'll actually see problems of both types on the exam whenever we get to that eventually. And so that's why I like to go over both types here in class, because it's also nice to be able to be flexible as far as how data is presented and how we can manage to work with it. All right. Now the last thing that we need to cover in this section, and it looks like we'll just be doing this one section today, which is fine. But the last thing we'll cover is what's called complementary events. Let me get the notation, make sure I get the notation right, because depending on textbook, different textbooks indicate complements different ways. In some cases they write a bar over the top of the event, and other times they write a little C for complement in what would technically be an exponent position, basically a superscript. So before we go any further, let me confirm which way this book does that, because I don't want to confuse you. My job is not to confuse you. Okay, so we use the little C. Gotcha. So suppose we have an event E. Okay. Its complement is written E complement. So we'll put a little C up here to show that we're looking at the complement of the original event. Okay. So, and the way that we define E complement is the list of outcomes that are not already included in event E. Okay. So everything that's not in E will then be in E complement. So if we go back to our numbers 1 through 10 in a hat, and we had event A was 5 and 10. Event B, we drew a 2, 4, 6, 8, or 10. In event C, we had the powers of 2, which is 1, 2, 4, and 8. Okay. What is A complement? Which event or which outcomes would be included in A complement? We know event A has outcomes 5 and 10 included. So the complement of A would be the list of outcomes that are not already included in event A. So of these 10 outcomes, we have 5 and 10 included here. Which outcomes would be part of A complements? Well, if we include everything that's not already included in event E, or A in this case, sorry, A has 5 and 10 already, so we want everything besides 5 and 10, which is 1, 2, 3, 4, 6, 7, 8, and 9. Okay? So 8 values, yes. For event B, what numbers would be in B complement now? There'd be 5 numbers there, right? We already have 2, 4, 6, 8, 10, so the complement would be 1, 3, 5, 7, and 9. Exactly, the odd numbers. If B is the even numbers, then the complement would be the odd numbers. And finally, for C complement, which numbers would be in this list? Three, 5, 6, 7, 9, 10, exactly. Okay. Yeah, so that's everything that's not included here. So here we have 1, 2, 3, 1, 2, 4, 8. And we look at what's omitted from that, which is the 3, the 5, 6, 7, and then 9, 10. Okay. So probability of A, we can see is 2 out of 10. We already calculated that. Probability of A complement, because we have 8 different numbers here, we know that's 8 out of 10. So 0.8. Probability of B, we know already is 5 out of 10, so 0.5. Probability of B complement also has 5 outcomes, so 5 out of 10, so 0.5. And probability of C is 4 out of 10, and for C complement it would be 6 out of 10. Should be 0.6. Okay. Notice what happens when we add together the probability of A and the probability of its complement. Probability of B and the probability of B's complement. And the probability of C and the probability of C complement. Point 2 and 0.8 is 1. 0.5 and 0.5, 1. And 0.6 and 0.4 and 0.6 also adds up to 1. Now it might seem like a strange coincidence, but if we think about how we came about, getting these results, again, we said the complement of an event is the list of all outcomes that are not already included in event E. So if we have the numbers 1 through 10 in a hat, if event A contains 2 of the numbers, its complement must contain the other 8 that are not part of the first one. B contains 5 numbers, its complement contains the other 5 that are not included here. That's everything else that's not already included in the first event. And if C has 4 numbers, then its complement has the other 6 numbers that we didn't draw. Okay? Now, what that means is that between the event and its complement, all 10 numbers are represented. Okay? So that leads us to another rule. This is what we call our complement rule. And this says that the probability of an event E plus the probability of its complement is always equal to 1. Okay? Because no matter how many different outcomes we have in a particular probability experiment, the outcomes are either part of E or part of the complement. And so between those two things, it should account for 100% of the different outcomes, or 100% of the possibilities. Okay. Now, another way in which we can use this formula is we could also say that probability of E complement is 1 minus the probability of E. And what we've done there is we've basically taken this term and subtracted it over to the right-hand side. Because what this tells us now is that if we know the probability of E, we can easily calculate the probability of E complement by subtracting that from 1. So we don't have to go through and count everything. We could just take 1 minus the probability that we already know to be true for P of E. So sometimes we'll see it written this way, but this is the most helpful format, where usually we're given one probability to begin with, and we want to find the other one based on that. Okay, let's look at homework here. This is on page 269. Look at 5 through 12. Also 13. And 19. Let's see. Then also look at 29. $33. And 42. Okay. We don't do a whole lot with complement just yet in this section, but we will use it a bit more in the next two sections. We'd like to introduce it here, and there'll be a couple of problems, I'm thinking the 5 to 12 and those problems. There'll be a couple of those that include complement, but it's going to be one that we incorporate more when we move forward into other material. But we like to introduce it here so that we're a little bit better prepared for the later material. So, all right, that's a good stopping point since we're out of time. And so you all have a good weekend. Again, the project, remember, that's due on Tuesday, so some of you have sent that to me already, which is great. But please make sure you get it finished by then. I would work on the project first before doing homework, but I do hope that you are able to look at the homework as well. So, like I said, y'all have a good weekend. Take care, and we will do this again Tuesday. Have a good one.